Okay, so we learned in section 3.1 about how to use cofactor expansion to find a determinant of a matrix. And the cofactor expansion is applicable to a matrix of a square matrix of any size. So, but of course, if we had a very like it said in the numerical note at the end of section 3.1, it said that if you had like a 25 by 25 matrix and it were dense, meaning not a lot of zeros in there, to do cofactor expansion would take about 500,000 years to just use direct cofactor expansion. Obviously, we can't wait that long to compute a determinant. So we can utilize some properties of determinants to help us speed up finding determinants. We can use these properties in conjunction with cofactor expansion. So there are three key properties in theorem 3 for properties of determinants from section 3.2. One is if a multiple of one row is added to another row to produce a matrix B, then the determinant of B equals the determinant of A. The next property, B, is if two rows are interchanged to produce matrix B, determinant of B equals negative determinant of A. And finally, the third property is if one row of A is multiplied by some constant K to produce matrix B, the determinant of B would equal K times the determinant of A. These are the three properties. Now, I have a little example that reinforces those properties. I would recommend you have your ebook open to section 3.2 so you can refer to this theorem as we go over this example. So here we go. Okay, discuss the three properties of determinants with an example. Or I should say probably, let's see here. Yeah, that's fine. Let me give you a moment to copy this down. Okay, so what we want to do is these three properties of the determinants from that theorem in section 3.2, theorem 3. It's nice if we can have just a little example to help see the properties rather than just we see these statements about the properties, but let's back it up with an example. So here we go. What I'm going to do is I'm going to define the matrix A as the 2 by 2 matrix given by first row is 1, -2, second row is 5, 7. What I'm going to do is I'm going to do a row operation on matrix A. So we like zeros generally in our matrices. Okay, so what I'm going to do is I'm going to use the 1 as a pivot to produce a 0 where the 5 is. So the row operation is I'm going to take -5 times the first row, add it to the second row, and that sum, the second row will be replaced by that sum. All right. Now that is the type of operation they're talking about in theorem 3A. If a multiple of one row is added to another row, okay, to produce a new matrix B. So A is equivalent to this matrix B. It's row equivalent to the matrix B. Let's look at the determinants. So the determinant of A, and I'm doing it for a 2 by 2 because it's easy to find the determinant of a 2 by 2. The determinant of A is 17, and the determinant of B is 17. Okay. So this reinforces, hold on here. I mean, it's absolutely amazing. Determinant of A, therefore, equals determinant B. Are there any questions? So this is just an example. It's not, it doesn't prove the result. It doesn't, I mean, theorem 3A, hold on here. Okay, theorem 3A, there it is. There's the result. The little example I did reinforces that theorem 3A result. It's not a proof, but it reinforces it. And so with an example like that, hopefully you'll remember the theorem 3A. Okay, let's go now to, hold on here. Are there any questions so far? Scaling, well, all we didn't do any scaling. This row operation here is a multiple of one row added to another row to produce a row equivalent matrix B. There wasn't scaling done, but let's see what scaling would do. Let's see. Let's go here now to, well, no, before we do scaling, let's look at property B, where property B, it says if rows are interchanged, if rows of a matrix A, if two rows of a matrix A are interchanged to produce a matrix B, then determinant of B equals negative determinant of A. In other words, let me be very clear. Hold on here. Let me just, so I'm kind of going back and forth between the book. So what we're doing now is I'm trying to convince you that theorem 3 result B is true. If we interchange two rows of a matrix to produce a new matrix B, the determinant of that matrix B is negative times the determinant of A. And here's a little example to reinforce that. Here's a little example. So hold on here. There we go. So there's the matrix A. Right. That's right, Mikhail. That's right. And we're going to switch rows 1 and 2. We're going to do a row interchange. And you'll notice that the determinant of A is 17 and the determinant of B is negative 17. So therefore, the determinant of B equals negative determinant of A. Please let me know if you have any questions at all. Okay. All right, well, let's go back to the book again. Now we're going to look at the last rule. Okay, here it is. The rule, the last rule in theorem 3, says that if one row of A is multiplied by K to produce a matrix B, that's a scaling, then the determinant of B equals K times the determinant of A. Okay, let's go ahead and look at the example that reinforces that idea. That's property C. So in this example, I multiplied 4 times row 1 and replaced row 1 with that result to get the row equivalent matrix B. That's a scaling, right? So the determinant of A is 17 and the determinant of B is 68. So indeed, the determinant of B is 4 times the determinant of A, because we used a scaling of 4. Are there any questions on that? All right, well, we can use these properties of determinants to help us compute determinants of large matrices or matrices that, for instance, are dense. They don't have a lot of zeros. I mean, let's look at an example. Let's look at an example. Okay, take a moment to copy this example down. We got a 4 by 4 matrix here, and it's a dense matrix. So if we were to use cofactor expansion, direct cofactor expansion from section 3.1 on that matrix, it would take a lot of time to do. We're going to find the determinant using row reduction to echelon form. So let me give you a moment to copy that down. Okay, so once again, we have this dense matrix A here, but we know that if we get a matrix into echelon form, it's very easy to compute the determinant. So we're going to do row reduction on the matrix A to echelon form and compute determinants as we go. I'll show you how this works. So what we do here in our solution is, well, go ahead and What I'm going to do here is I'm going to demonstrate the different properties. Okay, so if we look at the first row here, if we look at this first row, you can see what we did was we took 1/2 times the first row here and replaced the first row by that result. So if we think of, I mean, this matrix here, I should say it's a determinant. This is the determinant of B. So the determinant of A is 2 times the determinant of B, because the determinant of B is equal to 1/2 times the determinant of A. That's property 3C, theorem 3, property C, applied once. So really, it's easiest to think of it as determinant of B is 1/2 times the determinant of A. But then you could say determinant of A is 2 times the determinant of B, and this is what we have here. So far, are there any questions? All right, well, let's now think about getting the matrix in echelon form and compute determinants as we go. So naturally, in the first column, you see we have a 1 here, and this is why I did the scaling here. I did that scaling so I could get a 1 in that pivot position. Okay, and so now let me just see here. Hold on. One moment. This is a 3 here. Yeah, now what we're going to do is endeavor to get zeros, excuse me, where the 3 is here, and the -3 is here, and the 1 is here. And I do that by doing these row operations. -3 times row 1 plus row 2, you replace the result in row 2, and then you have the other 2 row operations. I mean, you've done this plenty of times, you know how it works. And by doing that, you get zeros in those spots in the first column. Remember, we're trying to get the matrix in echelon form. But how does that affect the determinant? Well, the determinant of this matrix here, right? That determinant is equal to this determinant. Because the row operations that were done here are all row operations such that a multiple of one row was added to another row. That falls under theorem 3A, and that means the determinant doesn't change. The determinant does not change with those kind of row operations. Are there any questions up to here? All right, well, let's continue. Let's continue. So now, obviously, we want to get a 0 where the -12 is. So I'm going to take that pivot of 3, well, that second row, right, and multiply it by 4 and add it to the third row. Again, the determinant is non-changed. This determinant here is the same as this determinant, right? These determinants are equal and these determinants are equal. Because we're just using theorem A. Now we've used theorem 3A. We've used theorem 3 properties A and C. Let's try property B out. So property B, what did I do here? Well, let's see. One moment. Oh yeah. What I do here? What I do is I take the second row, the third row and the fourth row, and switch the rows. I do a row interchange. Okay, swapping rows 3 and 4, and by theorem 3, property C, or property B, if you interchange the rows, that introduces a negative. So this determinant here equals the negative of this determinant. Those are equal. You see how this is working? Okay, Mikhail's seeing that. Jonathan's seeing that. Lastly, now what we want to do is we want to get a 0 where the -6 is, so we can get our matrix in echelon form. Of course, then we're going to use the -3 here as a pivot. We're going to multiply the third row by -2 and add it to the fourth row. Okay, so we're applying theorem 3A once again. May I go to the next page and show you that? Okay, Jonathan's good. Marcella's good, all right. Bellen's good, wonderful. Okay, well, Mikhail's good, wonderful, wonderful. So here we go. So there's the, of course, I just keep the, the 2 and the -1 there, and now there's my determinant of that. It was the same as the previous determinant, and now we have it in echelon form or in triangular form in this. And so the determinant then is just going to be the product. It's just going to be the product of those diagonal entries. And we actually saw that in an example, right? We saw that. We just saw that in an example. Okay, so you get 2. Well, I'm sorry, hold on. Let me clear that. I mean, there's the product of the diagonals, diagonal entries. There it is down here. And you had the 2 and the -1 before that. So -36. Okay, now what I want to do is I want us to do you know, this made it fair. This made it quite easy to compute the determinant. Cofactor expansion for this example would have taken quite a bit of time. We'd have to we'd have to have determinants of 3 by 3s, and I mean it's no big deal. I mean it isn't a big deal, but you can imagine if you had a much larger matrix, how much work would be involved in cofactor expansion. Okay, so let me show you another way that doesn't involve factoring. Yeah, well, Mikhail, so like this example, when we work this out, okay, when we work this out, we had, hold on here. We had this basically, we had this factoring, okay? You can think of it like as, you can think of this as a factoring step. But we can do the row reduction without that factoring step. So let's look at it now. Let's look at it a second way. The second way that we're going to reduce this, okay, involves, hold on here. The second way involves no factoring, only row replacements and row interchanges to compute the determinant. So what I do is I say, okay, I like the bottom row because the one's a pivot. So let me interchange that with the top row. And that's what I do here. And of course, by property B, that introduces a -1. So we're not going to have a factoring step. We're not going to do any scaling for this second way. Then, of course, we're going to use that 1 as a pivot. Well, we're going to use the 1 as a pivot to produce zeros in the entries below the 1 in that column. So here are the we do these 3 row operations. And the determinant doesn't change. All right, and next we want to have, we're going to use the 3 as a pivot to produce a 0 where that -12 is. So 4 times row 2 plus row 3, put the result in row 3. Again, that's another application of that row operation goes with theorem 3a. And so the determinant doesn't change. Now at this stage here, the third row has it has a 21 in the pivot position, has a 21 there. I don't want that 21 to necessarily be there in that pivot position. Okay, as a human being, I don't want the 21 there. I want the 6 to be there. So I'm going to take rows 3 and row 4 and interchange them. And that will produce then another negative. that will produce this negative here. And notice, run here. Let me just see here. So we've had two row interchanges. So we have -1 to the second power. Okay, -1 to the second power. So hold on here. Yeah, that's fine. That's fine. Are there any questions so far? Well, and how we got that -1, let me hold on here, clear that for the moment. So how do we get that -1? All right, keep in mind, you're talking about this -1, right? Okay, very good. What we did was we took row 3 and row 4 and we interchanged them. We did a row interchange. And when you do a row interchange by, let me see, it's, which property is that for theorem 3 from section 3.2? It's property B. When you interchange the rows, that introduces a negative. So in other words, what I'm saying is this determinant here equals -1 times this determinant. They are equal. Get that off there. Clean this up a little bit here. There we go. Belen, does that help you feel comfortable? Are you comfortable with that? Good, good. All right. Are there any other good questions? Okay, well then let's proceed on. Let's proceed on. So we have to get the matrix in echelon form in order to use in order so that the determinant is the product of the diagonal entries. That means we can't have a 0 where the 21 is. So I'm going to have to take the third row and multiply it by -21/6 and add it to the fourth row. And that's what we do. That's the row operation. And it doesn't change the value of that determinant because you're applying theorem 3A, property A. Now we have a matrix in echelon form, which we do, and it's echelon form, it's upper triangular, so we use a U for upper. Okay, and we have our diagonal entries now. Here they are. So the determinant of this 4x4 matrix is just the product of the pivots. Okay, the product of those pivots. Now I have to make the section 3.2 homework available. Likely I'll have we have 3.1 due on Monday, 3.2 also, but I have to decide whether I'm going to do, free response and multiple choice or just free response. I'll figure that out, but I'll just be aware that probably there'll be for Monday 3 or 4 assignments due. Okay. All right, so we really now have a formula here. We really, I mean, we really have sort of a kind of a formula, right? The determinant of a matrix ultimately equals -1 to the power, where the power is the number of row interchanges that were made, times the product of the pivots when the matrix is in echelon form. And most computer programs that compute the determinant of A for a general matrix use this approach. That's in the numerical towards the end of section 3.2. Well, not the end. We still have more to talk about really for section 3.2, though. We still do have more to talk about. So maybe I'll hold off on that assignment for 3.2 for Monday. Maybe we'll, have that due Wednesday. Mikhail, what did you say? Sorry. The stuff in part C, if it's ever used. No, what I am excluding part C. You're right. For this example, I did. And let me show you this formula on page 173 in the text. Let me just get it here. This example motivates this formula. All right, so let me go over here. Are there any questions on that? Okay. Let me go here. So you see, this is now a formula for finding the determinant of a matrix A. Get the matrix in echelon form. Record how many row interchanges you're using. That's R stands for, they're using R to stand for interchanges. It makes sense. Okay. Take -1 to the rth power and multiply it by the product of the pivots of the matrix A when it's in echelon form. How many think that's absolutely fascinating? The fact that we can compute a determinant this way using that formula. Yeah, I hear you, Mikhail. I hear you. And in the numerical notes, hold on here. I want to get to the numerical notes. Hold on. Where was I? Just give me a moment. I always let me just find it here. I'm sorry, class. Let me find it. Doggone it. Just bear with me for a moment, okay? Bear with me for a moment here. I'm trying to find that that numerical note here. That there it is. There it is. There it is. So it can be shown that evaluation of a determinant using row operations requires about 2 times n cubed over 3 arithmetic operations. And that means that for that 25 by 25, size 25 by 25 determinant, any computer compute that determinant in a fraction of a second. And that's the programming behind software like MATLAB when they compute a determinant. So how about that? How many like that? Isn't that good? I mean, how many think that's really, really cool? Yeah, Mikhail's liking it. Who else? Who else likes that? Yasin, excellent. All right, thank goodness for section 3.2. And this is where, we love computers, but we can't ignore math, because math helps us. It helps the computers evaluate faster using math. So excellent. Are there any questions before I stop the recording? Okay, I will stop the recording.